first video from chapter 26. It's going to be a quick motivation, and then we're going to define electric potential energy. And this is mostly in chapter 26.3 of the textbook. Okay, so just a little bit of motivation. So in general, a good rule of thumb is that scalars are easy, vectors are hard, right? So scalars don't have any directions to worry about, it's just a number. Vectors have all these pesky components and things to keep track of. So in general, if you can work with scalars, it's going to be easier than working with vectors. So this is partially the motivation for what we had for last semester when we looked at work and energy, right? The nice thing about work and energy is that it was a scalar. And in a lot of respects, it was a lot easier than working with all the vector components with forces. All right, so there's an analogy with gravity. So if you remember, again, this back to last semester, we talked about the gravitational force. So, and if we have two objects with mass, right, we can use Newton's universal law of gravitation. So negative g times the first mass times the second mass divided by r squared. So this is the vector force. Well, we could also define the gravitational potential energy. So remember, in general, gravitational potential energy, well, we ended up integrating the force, the universal force from the universal law of gravitation, and it looked like g times the first mass times the second mass over r. Now, what we can do is and we didn't talk much about this last semester, but in analogy to the force, you can define the field. So just like the electric field, we can define a gravitational field. And basically what you do is you divide out one of the masses, just like we did with the electric field and dividing out one of the charges. Now, what we can do, similar sort of thing with the gravitational potential energy, if we divide out that mass, one of those masses, we can define the gravitational potential. So that's what we're going to do with electric to define electric potential, but before we get there, we need to talk just briefly about electric potential energy. So, the electric force is a conservative force, and that's important. So remember, a conservative force, the work done only depends on the initial and final position, not on the path you take. So remember, things like gravity were a conservative force. Things like friction were not a conservative force, but the electric force is conservative. So, and if we have a conservative force, we can define a potential energy to go along with it. So in general, potential energy, well, it's negative of the work done by the force. So we want to do an integral from some initial position to some final position of the force dotted in with your path length element. So if you do this for two charges, well, the electrostatic force is Coulomb's law, so K QQ over r squared, and you integrate that with respect to dr, and you wind up with an electric potential energy of K times the first charge times the second charge divided by r. And again, the convention is the same as what we had with the general form of gravitational potential energy. As r goes to infinity, then the electric potential energy goes to 0. So a couple of comments. So if you remember, in a lot of respects, the electric potential energy works almost exactly like the gravitational potential energy, only we have charges instead of masses. And it can, well, and the directions are a little more complicated. But just like gravitational potential energy, only changes in electric potential energy are physically meaningful. And so this means that in general, at some particular location, the electric potential energy can be negative, right? Just like the gravitational potential energy can be negative. It just depends on where you define 0 to be. And just like with gravitational potential energy, for electric potential energy, if we've got a bunch of point charges, well, we can calculate the work done by the electrostatic force to assemble everything, or equivalently, you find the electric potential energy for every possible pair, and then do the